Next, we'll use what we've learned to express reaction rates. Example 15.1 says, consider the balanced chemical equation. H2O2 plus 3I minus plus 2H plus yields I3 minus plus 2H2O. In the first 10 seconds of this reaction, the concentration of I minus drops from 1 molar to 0.868 molar. Calculate the average rate of the reaction in this time interval. That's part A. And part B says, determine the rate of change in the concentration of H plus, that is delta H delta T, during this time interval. To work part A, we'll use equation 15.5 to calculate the average rate for the reaction. We were given information with regard to I minus. The concentration of iodide drops from 1 molar to 0.868 molar over 10 seconds. We calculate the rate with respect to one of the reactants by putting a negative in front and then 1 over the coefficient of that reaction, then the change in concentration over change in time. So we see that the rate with respect to iodide would be negative 1/3 times 0.868 molar, that's the final concentration, minus 1 molar, that's the initial concentration, over the time interval of 10 seconds. We weren't given a final minus initial time, but we were given the interval 10 seconds, so that's our change in time. We calculate the rate then as 4.40 times 10 to the minus third molar per second. Part B asks us to determine the rate of change in the concentration of H plus, that is delta H delta T, during this time interval. So what they're asking us to do is to express the change in concentration in terms of H plus. So we can use the rate that we previously calculated and the rate equation with respect to H plus to get the change in concentration over the time interval for H plus. So the rate is equal to negative 1 over the coefficient of H plus, which is 2, times the change in concentration over change in time. So we're looking for the delta H delta T, and so we can solve for that if we know the rate. So delta H delta T is equal to negative 2 times the rate, because we multiply both sides of the equation by negative 2 to isolate delta H delta T. So delta H delta T is equal to negative 2 times 4.40 times 10 to the minus third molar per second, which is equal to negative 8.80 times 10 to the minus third molar per second. For practice 15.1 reads, for the reaction shown above, predict the rate of change in concentration of H2O2 and I3 minus during this time interval. So we're asked to calculate the same thing for hydrogen peroxide and the I3 minus species. So we can use the same information, we can use the same rate to perform this calculation. So for hydrogen peroxide, we see that the rate is equal to negative, and the coefficient here is just 1. So negative 1 over 1 times the change in concentration of H2O2 over delta T, which is, this is what we're looking for. And that's equal to the rate, which was previously calculated as 4.40 times 10 to minus third molar per second. So in order to isolate delta H2O2 over delta T, we just multiply both sides times negative 1. So we get delta H2O2 over delta T equal to negative 4.40 times 10 to minus third molar per second. Next, we'll calculate the same thing for the I3 minus species. We see that the rate is equal to, the coefficient for this one is also 1, since this is a product, we use plus instead of minus. So plus 1 over 1 times the change in I3 minus over change in time is equal to 4.40 times 10 to minus third, the previously calculated rate. So since this is a positive, the change in I3 minus concentration per change in time is just equal to the rate, which was 4.40 times 10 to the minus third.